Okay, all right, ladies and gentlemen, welcome back to another leetcode stream. We are still the same. Let's get this done today. Okay, we are live. Perfecto. Let's get two questions today of leetcode and some system design concept. Maybe we'll learn consistent hashing today. Okay, minimum operations to make a uni-value grid. You are given a 2D integer grid of size m by n and an integer x. In one operation, you can add x to or subtract x from any element in the grid. A uni-value grid is a grid where all the elements of it are equal. Return the minimum number of operations to make the grid uni-value. If it is not possible, return -1. Okay. Okay. One operation. Okay. So I can do this operation many times on one item. That's the key here. So for example, let me open this shit up. So here x is 2, right? I can add or subtract 2 from any of these any number of times. Let's say I want to make all of them 0. So how many operations will that take? So -2 for this one operation, -2 twice here, -2 4 times here, and -2 3 times here. How many operations? 3 plus 4 7, 8 9 10 operations if I want to make all of these numbers to 0. Now let's say what is the closest number to all of these? That's a good point. Should I take just average? But average might not be I don't know, man. Yeah, I can add 2 here. This is one operation. I can subtract 2 here, and I can subtract 2 twice, so it'll be 4 operations. Now the average of this, not the average, the median, right? Average is a okay, median, right? Do I need to find median? 2 4 6 8. What is the median? So in a sorted array, if the numbers are even, I mean if the number of items are even, it is the average of these middle two numbers. That is the median, right? So 6 plus 4 divided by 2, which is 5. So I can't make all of them 5, right? So either I choose 6 or a 4. Okay, when x is 1, I can do a lot of stuff. Am I thinking? Am I overthinking this? Is it an easy question? I don't know. So this 2D integer grid, I don't know if it makes any sense to keep them in a grid. If it is a single array, that also just makes proper sense, right? It's the same number of things. Yeah, I mean, if I keep all of them in a single array and choose one of the two middle values, right? Let's say I pick this 1, 2, 3, and 5. 1, 2, 3, 5, and x is 1 here, right? X is 1, so I. Okay. But it also, let's say if this was, I don't know, man. If I don't know if median would actually work. I'm not exactly sure. But let's say if I chose 2 here, I can add 1, I can subtract 1, and I can subtract 3 from here. So it will be 3, 4, 5 operations. But if I chose 3, I'll add 1 here, I'll add 1 twice here, and I'll subtract twice. So it is still 5, right? So is it 5? Yeah. 1, 2, 3, and 4. 1, 2, 3, 4. And x is 2. Now let's say I chose one of these two. Let's say I chose 2. If I add 2, it doesn't make this 2, right? So no. So this is not possible. We return -1. I believe this is the solution, man. Just pick any of these. Either choose this or choose this and get the minimum. Okay, let's see if it works, man. So instead of keeping it in an m by n thing, I'll just keep them in a simple array, right? Int combined equals new int m times n for int I equals 0, I is less than m I plus plus. Okay, arrays dot sort combined yeah. Now I need to pick the middle two elements. Now if p is odd, it can be odd when it is like 3 by 3. There are 9 numbers, so it is p is odd, right? So if p is odd, then return get minops in from combined. P is odd, right? So let's say if there were 5, so 0, 1, 2, 3, 4, size is 5, so 5 by 2 is 2 is the level. Okay, so just return, get the p by 2th element combined of p by 2, or just simply return p by 2, right? That's it. Else if it is even, then I can simply do this, right? Not math.min exactly. Okay. Int r1 equals get ops combined p by 2, r2 equals no. Is it p by 2 plus 1? Let's say if there were 4 elements, how do I get 4 by 2 as 2 for p by 2 minus 1? P by 2 and then minus 1. Now if r1 equals minus 1 and r2 is also minus 1, then return minus 1, else return math dot min r1 and r2. Now I just need to write this getops function, which will be an order of n thing, right? Int getops, int array, int m, right? It's private. What happened to the fucking in getops ops equals 0 for int. Why is the autocomplete not working, man? Have I clicked something? Int n in array. What? Why is upgrade to premium to use autocomplete? What the? No, not that autocomplete, man. I just need these braces and stuff. Okay. For every number, I need to check how far is that from I need x as well. So int x, let's pass in x in each of these. X, okay. Now what do we do here? Int median equals array of m, right? If diff equals math dot abs of n minus median, if diff mod x is not equals 0, then return -1, else ops plus equals diff divided by x, right? Maybe some syntax error. Yeah, what? Yeah, let's see if this works. Okay, yeah, it works. Okay, good question. Let's do one from leetcode. Maybe some difficult question, I believe. Let's see. Let's do from trees, man. Or let's do that thing. Median of two sorted arrays. Where is that? That would be median of two sorted arrays. It is binary search, right? Yeah. This question is amazing. This question is the shit, man. So, given two sorted arrays of nums1 and nums2 of size m and n respectively, return the median of the two sorted arrays. The overall runtime complexity should be log of m plus n. Okay. Now, this question is fire. This question is the shit, man. Okay, let's take this example. And the examples are also shit. So we'll make our own examples. Okay, let's extend these guys. Okay. Now you see there are two arrays, 1, 3 and just 2. Let's extend them 1, 3, 4 and 7. And let's say this is 2. Are there unique numbers? No, that's not certain, right? Let's take this 2, 3 and 6. I want to find the median of these two. Now, one way is to combine them and just get the median, right? But the time complexity says just log, not even order of m or n, right? So we can't traverse these two arrays. That's the key point here. Now, since this is the time complexity, it is definitely going to be a binary search, right? Now, from these two sorted arrays, we know the minimum and maximum element in the combined array, right? So we get the minimum by comparing the first elements of each array. So it'll be minimum is 1 and max is 7. Now, do we do a binary search between 1 and 7? Is that the case here? No, I mean, we pick the mid element of min and max, which is 4. And we see if we can find 4. It was something like that. I mean, I don't remember the solution exactly. This question is just like if you know it, you can do it. Otherwise, there is no chance. There is absolutely no chance that you can figure this out on the spot in an interview. This kind of question is just that. So, as far as I remember, we pick the mid element from these two, and then we try to find using binary search, and then we check some shit. That's the key point. Or do we just take the middle elements of these two? I don't know. So I can't recall. I can't recall my older solution, so I'll just take a look. And this is such a shit runtime, man. This is even shitter runtime. Why are all of these so worse? Okay. Okay, so first thing to make sure is keep the nums1 array always smaller. Now we get the size. Total is n1 plus n2. If n1 is 0, then m equals n2 by 2. If it is this, then that, then that. Okay. Half equals total by 2. What is... okay. We get the mid value. I mean, okay. L is -1, R is n1. While true, m1 equals L plus R by 2. m2 equals... okay. Oh, okay. So, okay. It goes something like, we just imagine that these two are combined in an imaginary array, right? Then if the size of this was 4 and this was 3, the total size of the combined array would be 7, right? Now we do a binary search on this, right? We do a binary search on this combined array. So we do binary search starting from 0, right? Why are we taking L equals R equals n1? Half equals total by 2. Okay. 7 by 2 is 3. This is half. Now we set L as -1 and R as n1. L is here and R is... okay, I messed up. So the point is, this is, since this is smaller, so this will come first here. This is bigger, so this is n2 basically. So n1 is 3, n2 is 4. R is this, n1. So R is here. Now what do we do? While true, m1 equals L plus R by 2. Yeah, so R is at the starting point of the next, basically, yeah. Okay. Now we get m1, which is L plus R by 2. L plus R, -1 plus 3 minus 2 by 2 is 1. This is m1. Then we get m2 by half minus m1 minus 2. What does that mean? 3 minus m1, 2 minus 2. What? What is half minus m1 minus 2? What does that mean? Half minus m1. 3 minus 1, which is 2, minus 2, which is 0. I can't figure this out, man. M2 half. Let's see some solution. If we cut the sorted array to two halves of equal lengths, the median is the average of max of lower half and minimum of upper half. Yes, that makes sense. The two numbers immediately next to the cut. For example, 2, 3, 5, 7, we make the cut between 3 and 5. Yeah. Then the median is this. Note that slash represents a cut and numbers, now number represents a cut made through numbers. Okay. Oh. Yeah. It's not hard to conclude that index of L equals n minus 1 by 2 and R is at n by 2. Thus, the median can be represented as L plus R by 2. A of n minus 1 by 2 and A of n by 2 divided by 2. To get ready for the two array situation, let's add a few imaginary positions represented as bounds in between numbers and treat these numbers as positions. Okay, this is getting complicated, brother. Let's see this. I think I need to watch some YouTube video, man. I can't understand shit. Median of two sorted arrays.
Hey everyone, welcome back. Let's write some more neat code today. So today let's solve a pretty difficult problem, median of two sorted arrays. So we're given two arrays, nums1 and nums2, that are already in sorted order, but they could be of different sizes, m and n. And we want to return the median of both of the arrays when they have been put together and sorted. So not individually, but we want to put them together and then find the median of both of them. And not only that, but we want to do it efficiently. So log of m plus n worst case, right? So one example, we can see one array could be 1, 3, another array could be 2. And in this case, when you put the two arrays together, it's pretty obvious that 2 is the median. The median is the middle value. Now we know that there are other examples where we might have an even number of total elements, 1, 2, 3, 4. When you put those together, we get 1, 2, 3, 4. In this case, we have two numbers that are in the middle, 2 and 3. So what do? We can just take the average of these two. And we know the average is 2.5. 3.5. But both of these examples use a merged array. But we know if we actually merge two arrays together, like 1, 2, and 3, 4, the worst case is actually big O n plus m. And that's not log. Use array
Yeah.
B, and let's call this array A. So we know we can merge these two arrays, right? And then the median is obvious. But what exactly is a median? Well, it's the middle value, right? In this case, this is the middle value, and we know that because we know to the left of it, there are 6 elements, and to the right of it, there are 6 elements. So in this case, we have an array of 13 elements, and this happens to be the middle. The left partition of 6 elements is the same size as the right partition of 6 elements. So what we're doing is partitioning the array into 2 equal halves roughly, right? Because we know there's an odd case and an even case. Now let's just take hypothetically, this 8 doesn't exist. Then in reality, we have 12 elements. So we take the left partition to be 6 elements and the right partition to be 6 elements. So in that case, we know we can take the 2 middlemost elements, or in other words, the rightmost value in our left partition and the leftmost value in our right partition, and take the average. So add them together and divide by 2. We know that's going to be 3.5. So how can we simulate that without actually merging these two arrays? How can we simulate that with just the original arrays, which are still in sorted order, right? Luckily for us, they are given in sorted order. So keep in mind that the total number of elements we have in this case is 13, and half the number of elements we have is roughly 6. I'm going to round down in this case. And when we talk about partitioning, we want our left partition to be roughly equal to half. So when we partition this, we want the left to be roughly 6. So the most intuitive way to do this is, let's get half of the elements of, let's say, A, right? So I'm going to have a left pointer initialized here, and I'm going to have a right pointer initialized here, and I'm going to find the middle. So we know this is index 0, this is index 4. I add them together and average. So we know that the middle is going to be 2, right? So what are we actually going to do? So this is going to be our middle value, right? And basically what that means is our left partition is going to include that. So far, our left partition initially is going to be like this. Now, obviously, we can increase it by adding an element. We can also decrease it by removing an element. But initially, let's have our left partition have 3 values in it. So it has 3 values. Great. Now, can we repeat that same process up here? Well, the good thing is we don't actually need to, because look, in this case, if we do that, we're going to get 4. And we can basically, if we want, we can run binary search up here too. But is that even necessary? Because look at this. Half our elements are 6. So really what we can do is say half minus 3 over here is going to be equal to 3. So if we run binary search on just this bottom array, we can compute the size of the left partition for the second array, right? We can just compute it using our half value. And since we know 6 minus 3 is 3, we know initially we can say that the left partition of this is going to be 3 as well. We don't even need to keep a left and right pointer for this array. So these two sub-arrays make up our left partition. Now my question is, how do we know if we found the correct left partition or not? Well, we want them to be in order, right? So notice how we already know that this 3 is going to be less than or equal to the element that comes after it. That's what sorted order means. And we already know this value is going to be less than or equal to the value to the right of it, because this is also in sorted order. But we want to make sure that the left partition is less than or equal to every element in the right partition, and this is our right partition. So how can we determine that? Well, one thing we can ask is the right...
So why are we subtracting 2 here? I mean, I'm not sure about that, brother. Okay, m1 is L plus R by 2. Then half minus m1, which is half minus m1. 3 minus 1 is 2. Okay. Now there are 7 elements here, right? Half is 3. Now here m1, I found it to be 1, right? 3 minus 1 is 2. 2 minus 2. Okay. So we are taking L in such a way that we have to subtract 2 to get the fucking proper partitioning. That's the point. Okay. That is why we are subtracting 2. Okay. Okay. Yeah, makes sense. Okay, we get m1 and m2. So this is basically the first half. Now L1 is if m1 is greater than or equals 0, then nums of 1 m1. If r1 is okay, if m1 plus 1 is less than n1, then r1 is this, L2 and r2 respectively. Then we check. Interesting. Very interesting. Bro, I'm getting bored of this shit, man. Okay, I get the point. This is just bullshit, man. Okay. Then we check if L1 is less than equals R2 and L2 is less than equals R1, then get median of these two. Now in get median it will just check if total is odd, then return what? Minimum of R1 or R2. Yeah, makes sense. Okay, yeah. Thank you, leetcode. Thank you for explanation. Let's write this up. Int n1 equals nums1 dot length and 2 equals is it okay. Okay, nums2 of Okay. Okay. Good to revise this question again. I hate such questions, man. But it's fine. It's fine. Okay. Now let's get some system design stuff. What can we study? Let me see here. Okay. Let's revise consistent hashing and let's learn about vector clocks. Let's take two topics today. So, um, off stream, I learned about consistent hashing. So, what does consistent hashing achieve? First of all, uh, it achieves consistent data distribution among n servers and easy to scale, basically increase servers, increase number of servers with minimal redistribution of data. So these two things are achieved by consistent hashing. How does it do that? So it simply says, let's say we have 5 servers, 5 database servers where we need to store key value pairs or whatever. So instead of relying on, it's whatever, okay. So there are 5 servers. We map these 5 servers on an imaginary circle. We call this hash ring. And how do we distribute that? We maybe take the IP address of each server and map it to some value between 0 and 2 pi radians. Now here, when we get this value, we map that onto this hash ring. Let's take blue or whatever, this brown. Let's say the names of these servers were A, this was B, this was C, this was D, and some, there is no yellow here, man. Let's take this E. Now, easier way to explain this is we map each of these servers on this hash ring. Let's say this was A. Let's say this is B, C here, and then D, D here, and then E here. These servers are mapped on this hash ring, and then we insert our data points on this hash ring. Maybe there were like 3 data points here, 1 here, 4 here, 2 here, and let's say 3 here. Now we simply say that all the data points to the counterclockwise direction, basically from each data point we go to the counterclockwise direction and we check what server we encounter first. That data point gets stored there. So for example, this data point gets stored in A, this also in A, this also in A, but this gets stored in B, this gets stored in C. Yeah, similarly this in D, this in E. Now this is the easier way to explain consistent hashing, but there is a problem here. Let's say all of the data points were in this arc. That would cause a load on this server named D. So what do? Instead of just single points of server, we keep many points. We call that weight. Let's say if we define weight as 3, so there will be 3 A servers on this hash ring. It will be just abstract. Server will be only one, but these data points will be at multiple locations. Let's say there was A1 here and A2 here. Sorry, A2. Now, similarly for B, this was B0. B1 could be here. B2 could be here, and similarly for other servers. Now this will ensure that there is somewhat even distribution. Like we can see here, there are still 3 here, but B0 gets only 1, right? Maybe when there was data point here, this will go in A1. Yeah, there will be somewhat even distribution of data. Yeah, that's what consistent hashing is basically. What else is there? This 3, like A0, A1 and A2, this is called weight. We have to fine tune it. What am I writing, brother? Weight is 3 here. So yeah, okay. Yeah, this is consistent hashing basically. So we use for like a distributed cache, a key value data store, a scalable key value store solution, and maybe for databases. Who knows? Okay, now let's see what vector clocks are. Vector clocks. Let's not open Geeks for Geeks because it is the shittiest website ever existed in the history of mankind. Let's see. Oh, let's ask fucking Chat GPT, man. What are vector clocks? Vector clocks are a way of tracking the partial ordering of events in distributed systems. They are used to determine the causality between different events that happen in different processes or nodes within the system. This helps in detecting whether events are related to or whether they occur independently. Here's a simple breakdown of how vector clocks work. Vector structure. A vector clock is an array of counters, one for each process in the system. Each process maintains a vector of counters where the counter at index I represents the number of events that the process I has seen. What? Each event in the process increments. Okay, there's no way. Okay, let's read. Let's read it. A vector clock is an array of counters, one for each process in the system. Each process maintains a vector of counters where the counter at index I represents the number of events that the process I has seen. Event representation: each event in a process increments that process's counter in the vector. So if process I performs an event, it will increment its own counter in the vector. Vector clocks allow you to determine whether one event causally precedes another. This is done by comparing the vectors associated with two events. If the vector clock of event A is less than the vector clock of event B, meaning all of A's values are smaller or equal to B's, and at least one value is strictly smaller, then event A causally precedes event B. Consider a distributed system with three processes P1, P2 and P3. Each process has its own counter in the vector clock and they perform some events. Before any events, all of them are 0. After P1 performs an event, it updates its vector clock to 100. When P2 performs, it is 0.0. After P1 sends a message to P2, informs P2 about P1's event. P1 becomes 200, P2 becomes 110. Event local to a process. The process increments its own entry in the vector. Message passing. When a process sends a message, it sends its vector clock along with it. The receiving process will update its own vector clock by taking the component-wise maximum of the two vector clocks. Advantages of vector clocks: captures causality. They provide a mechanism to capture the causal relationship between events in the distributed systems. Detects concurrency. It helps in identifying events that are concurrent. Space complexity. Yeah. Communication overhead. Okay. Okay. Yeah, I kind of get it, but okay. What are Lamport clocks? What the fuck is a Lamport? Computers generally track the current time using a quartz crystal that oscillates at a known frequency. This frequency is used to advance the local clock at predefined intervals. Quartz oscillates with enough stability that it can be used to maintain time within a few milliseconds of accuracy per day. Over time, however, these imperfections can accumulate, making the clock inaccurate. To fix these inaccuracies, computers typically run a background process like NTP to synchronize the local clock with servers that are known to be accurate. This model works well when you care only about the time of a local computer, but fails when you need to compare events that happen on different computers to see which one happened first. Okay. You know what? I'll read this article offline and I'll be back tomorrow with a more proper explanation, probably. So, okay. I'll be closing the stream here. Thanks for watching. If anybody is here, I'll see you tomorrow. GG.